Hello friends, today we are talking about peak finding. So this problem is interesting, and it can be done for multiple types of arrays. So we have a version that is for a-dimensional arrays, another one for two-dimensional arrays. Okay, so let's explain the problem a little bit more. So we have, let's say, an array, the following array, that has elements A, B, C, D, E, F, J, let's say, and let's give it H, I, okay? And these have indexes, the following indexes. Okay, yeah, I'm just indexing from one, that's just for demonstration, so don't worry about that. And let's say we want to find the peak. So the peak is the element, let's say B is a peak if B is bigger than both of its neighbors. So its neighbors are A and C. So if B is bigger than A and is bigger than C, then it is a peak. So it's kind of when you have an element that forms something like this, where you have B here, A here, and C here. Okay. So let's look at it. Let's look at it in an array here. So let's say we have this array in a general array. So let's say we have this one where you have some elements. Let's start from index 0 this time. We have 1 and you have a bunch of elements, and here you have the element at position n divided by 2, and we go until we have the element at index n. So this means that the peak can be here, or it can be in the middle, or it can be like even in the last element. And so this right here represents being the peak at the top. Okay, so if we do just like the brute force, straightforward, simple approach, we can just walk the array from left until we find the peak element. And with this solution, we would get a worst case where the peak is actually at position n. So that would be worst case complexity for the solution 1. Worst case complexity would be O of n. But we can do better actually than this solution. We can apply something that is often known. So it is binary search. So we can apply binary search in this case. The binary search idea is to just take the middle element and reduce the problem with a certain condition. If that middle element doesn't satisfy that condition, then we just found the solution. If it is like less or something, we can just go to the left, or bigger, we can go to the right. So we can apply the same principle here. So we have our array that is, let's draw it here. So we have this array. So from 0, let's say we have 1. Let's start from 1 just to simplify our logic. We can code later with arrays that start with 0. And let's say we have n divided by 2 elements here. And we can go until we have the nth element. Okay. And here we have the n minus 1. Let's write this here. Here we have n minus 1 element. Okay, so first we look at the element at position n divided by 2, which is the idea of binary search, and we just take a look at that element, and we look at its left, the left element of it, and the right. So the left on its left is n divided by 2 minus 1, and on its right is n divided by 2 plus 1. So we can just look at those two. So we can check if A, which is this array here, of this position n divided by 2, is less than A of n divided by 2 minus 1, then we can just look at the left part, look at the left side. Now else, if we look at the if it's less also than the element on its right, then we can just look at the right side. Otherwise, that means that it's bigger than the element on its left and it's bigger than the element on its right. That means we found the peak element. That means that n divided by 2 is the peak element. And this gives us a really good solution, because whenever you can reduce a problem into a smaller size problem, especially like this where we just divide it by half, it's a lot better than our Venn solution. So let's look at the running time of this solution here that we just took a look at. So the running time of this is, if we take a look at it, so it's the total is, so let's just call the complexity of this T of n. So so we divide the problem by 2, so we get the complexity of the solution of n divided by 2 plus some constant factor. So whenever you have a complexity where of the problem where the solution just divided by 2 or reduces the problem to some sort, then you can just find the complexity by by calculating the complexity of the solution of the reduced problem plus the time it took to reduce the problem. So in our case, the time it took to reduce our problem is just the two comparisons that we did between the element itself and its left neighbor and right neighbor. So that's just two comparisons, and that's a constant time work. So that's what this O of 1 comes from. And if we go further, then we can just, this T of n divided by 2 is also T of n divided by 4 plus O of 1 plus O of 1. And we can do this, even continue doing this further. So it's T of n divided by 8 plus O of 1 like 3 times, okay? And we can go down, and at the end we will find that this is divided by we can find that that is just T of n divided by 2 to the power of k plus ck, okay? And with this we can see that if we replace n, if we substitute k with log of 2n, we can just find that t would be of 2 to the log of base 2 of n plus c of log base 2 of n. And with this solution we would get the final solution, which this would be just t of 1 plus c of log c is just a constant that I'm replacing this O of 1. So O of 1 is just constant work. I can just replace c with that, okay? Now this is log 2 of n multiplied by a constant, and T of 1 is just 1, so because finding the big element for one array element is just has one just constant time, so we can just ignore that, and this would be O of log n. There is another easy way to see it, because this one is just O of 1 plus, according to what we did here, would be plus O of 1 plus O of 1 until plus O of 1, and it would be log of 2n times, because each time we divide the problem into a problem that is half the size. So the number here is log of 2n. You can visualize this as just a tree where every time you go down like the left path or the right, and hence you divide the problem by 2, and the number of like the height of the tree would be log n. So that's what this represents. So at the end you would just have O of log 2 of n. And that basically how it is solved. And why is this better than O of n? that is a really simple explanation. So let's look at this. So O(n), say for example, if we have an array of 1000 elements, that means that it will say execute, say if each operation, if the constant time operation take like say just 1 second, just assume that for example, then the O(n) algorithm would take 1000 seconds to run, and the O(n) log(n) algorithm would take log of 1000, it will take just 3 seconds. So you can see the solution is a lot faster. So this is the idea. So what we are going to do now is we are going to first look at the implementation, and then after that we will go back and look at the 2D peak finding, which is the same problem but for a matrix, which is a 2-dimensional. Okay, so now we are going to take a look at the peak finding algorithm for 1-dimensional array for peak elements. So this problem is what we explained earlier. So a peak element is an element that is greater than its neighbors, left neighbors or right neighbors, and our goal is to find the index of the peak element. So we apply binary search in a way. So we initialize the lowest value, the low index to 0 and the high to array length -1, which is the last element index, and we initialize middle to 0. And while low is less than or equal to high, which is what the loop of binary search, and so we calculate or compute the middle index. So that is just low plus high divided by 2, and this is just an optimization so that we don't get the integer overflow problem. And so here is we take the before element as the minimum value, and after element also as minimum value, the before neighbor and the after neighbor. This is just to handle the case where we are examining the first element, which doesn't have a before neighbor, and the last element, which is at the index n-1, or the length of the array -1, which doesn't have an element after it. So we initialize those to min value because that will not prevent that value either at index 0 or index n-1 from being the peak if it's our only choice. And so what happens is that we look up the middle element we look up the middle element that we just got. If it's bigger than 0, which means it's after the first element, then we can compute before the neighbor that is before it, which is just array of middle -1. And for the case where we are not at the last element, we can compute the element after the middle, which is or the position that we just chose, which is array of middle +1. And then here we check if the index we are examining, which is the middle element here, is both bigger than the element before it and the element after it, which means that it's bigger than its neighbors, then we can just return its index. Otherwise, we can check if that element is less than the element before it, then we can just set high to middle -1, which will make us examine just the left side of the array. And otherwise, we'll just put the low value to be middle +1, which will just examine the right side. Okay, and that's it basically, and it will recurse and it will do the same thing but only on the left hand side of the array, and in this case it will do the same thing only on the right side of the array. And if we run this, we can find that it is working. So for the first one, it finds 10 here, the first element, 0, because it's bigger than 5 and there's no element before it. For the second one, it finds 4, 0, 1, 2, 3, 4, so it finds this one. It's the only one that is peak. And this one is 0, which is same thing. This one is bigger than all of them. So if we put this to 10, this probably should be 1 here. And if we look, yeah, so it's working. Next we'll take a look at peak finding for a 2-dimensional array, which is basically just a matrix. So let's continue on peak finding for a 2-dimensional array. So This time we are going to see it for a two-dimensional array, which is just a matrix. Okay, so let's see how does it look like. So let's say we have this matrix here that has the element 0, 3, 2, 0, 0, 4, 1, 0, 0, and let's just say 5, 0, 0, 0, pick 0, 6, 0, 0, 0, and 0, 7, 8. Okay, and we want to find the peak element of this. So the peak element is what, let me just first give you the definition of a peak element. So if we have this matrix here with, say, a couple of rows and columns, and we have, this is A, and we have above it C, D, and let's say instead of D here we have, so we have here B, we have D, and we have E. So I is a peak, A is a peak if only if A is bigger than B and A is bigger than C, A is bigger than D, and A is bigger than E. So basically only if A is bigger than all of its neighbors. So A bigger than all of its neighbors, or direct neighbors, let's say. Okay, so this is how it looks like. Now how can we find the peak element of this? So we know how to do it for 1D. So one solution that you might think of is just pick a column, like a middle column of the matrix, and then so this is the first step, and then after that do a find one peak that we did earlier, found 1D peak on that column of the middle column, and the third step would be to basically to do the same recursion that we did for the 1D peak finding, by just if it's like less. So if the one peak here, the peak that we found here, let's call it P, if it's less than its left neighbor, then we go left and recurse left, and if it's less than its right neighbor, then we just go right. Okay, so this may seem like it works, but actually it doesn't. It's incorrect, because suppose you found a 2D peak, let's say for this one here, okay, and you go to the left, okay, until you find one where left neighbors is, and so you go here, and so you find, but this is not necessarily the peak of this column. So this is not necessarily the peak of this column, so you may get an incorrect solution. So this is not correct, but it's very similar. The right solution is very similar to this. So the only change that we need to make is to this step here, the second step. So how it works is this way. So first we pick middle column, so that step stays the same. Let's call it J. So our matrix here has, like, let's say it has m columns and it has n rows. Okay, so what would happen here is that we would pick the middle column, which is J, which is equal to m divided by 2. Okay, and the second step would be, instead of using the instead of using the 1D peak finding, we can just pick the maximum element of that column, which is the biggest value, which means that it would certainly be the peak of that column, but it has also the property that it's the maximum value. So we'll pick max of column J. And the third step would be also the same. So it would be checking if the left neighbor and right neighbor. So this max column here, let's call it max just. So if max is less than left, then recurse left. And if max is actually less than right side, then we recurse right. Okay, what does recurse mean? So recurse, if we say, for example, take this column, which is the middle column, and apply to it the algorithm, so we would find the max at the position, at this last position here, so 8, and so 8 is bigger than 7 and bigger than 0. So this is a bad like example. So let's say, for example, we change this to be like 5. Okay, so we pick the max, which is this is less than the left element, so we would recurse on this left side here, which means we will pick the middle column of this, but since this is just 2, so middle we can just pick this one or this one, so let's pick this one. And so here the max is 7. 0 is less, so we don't recurse, and so we find the peak element. If, say for example, we had here let's say 7, if we had here 7 and we had here, let's say 10 4, for example, or something like that, we would go to the left and we would pick this one, and it would be we would check the max and it would be this one. Okay, now else, which is the other case, which means that max was both bigger than left and bigger than right, that means we found our peak element. That means that max is a peak. Okay, so this problem also means that on every iteration we divide the problem by half, because we pick the column, the middle column, and we check the max, and then we recurse either to the left or the right, and doing that we reduce the problem to its half. So this actually it is intuitively correct. If we look at it, it does matches actually the 1D version. Plus, with a single column, we find the global mask, which is max. So, for example, which is its own peak. So let's look at the complexity of this for a second here. So, complexity is Tn of. So we divide the problem by 2 by picking so the rows are unmodified, but the columns are reduced by half. So we have m columns, so we divide by 2. So this is the rule that says the runtime of an algorithm that uses divide and conquer here is equal to the runtime of the reduced problem plus the time that it took to reduce the problem. So the time that it took to reduce the problem here is just O of n, because it's the time that it took to find the max element in this step here. And that is just by going through the entire column, which is the number of rows, so it's O of n. And if we take a look at the base case, which is so this is actually not just T of n, because this is parameterized by both the number of columns and number of rows, so T of n m. So if we look at the base case, which is the case where we have n rows and one column, so the case where we have just one column, so finding the peak would be just finding the max, right? So this would be just picking the max, which is O of n. Okay, now so this is the base case of our analysis here. So that means that this actually is T of n m is O of n. So we would divide this T of n m2 to another just problem, which would be T of n m divided by 4, and another one which would be T of n m divided by 8, and it will follow the same thing that we did, the same analysis that we did earlier for the 1D peak, where we would arrive at this here, and at the end we would have T1 plus a constant multiplied by that. And if we define it in a way, we can have, so it would be similar to, so it would be O of n plus O of n plus O of n, and it would be how many times? It would be log base 2 of m, which means that the final solution would be O of n, log 2 of m. Okay, so this is the final solution. Runtime, which is not bad at all compared to an O of n m algorithm that we can find. It's called the greedy ascent algorithm, but it's I'm just skipping it because it doesn't have any real value actually. So we find this solution, which is pretty good. Now next we will take a look at a real implementation actually of this algorithm on a 2D matrix. Okay, let's do that. At peak finding, 2D peak finding, so it's just finding a peak element on a 2D array, so in a matrix here. So I have written a solution here. So we have this matrix that I want to find the peak element of. So what we do, so first I'm just going to get the number of rows and number of columns from the matrix, and since we are going to do the same style binary search, we just initialize low and high indexes, and then we initialize the max index, which would be the max of our column that we will do on each step, and we have the middle value, which is equal to 0. And so while we haven't explored the entire matrix, we keep iterating. So we calculate the mid element in the same way, low plus high divided by 2. And remember, this optimization is just for against integer overflow. And we find the maximum element of the column. So we pick the middle column. So this is picking the middle column here. And then we find the max of that column with this helper function here. That takes the matrix, rows, and the column for which we want to find the max, and just goes through each element in the column, and it picks the max. That's all it does, and it gets only the index of it. And so what we do is we check, of course, the boundary case that mid minus 1 is bigger than 0, that we didn't get to the last last column, and because iterating to the left in that case doesn't make sense, and we check the element before the middle, and the element we check the element before the middle, which is the left neighbor. We check if it's bigger. If it's bigger, then in that case that means we need to recurse on the left side, and we do that by setting the high index to mid minus 1. If however it's the element on the right, which is its neighbor on the right, is the one that is bigger, then we recurse on the right side by assigning to the lower index mid plus 1. And this check here is just to check that we are not on the last column, because if we are on the last column, there is no use of checking or going to the right side. We are done basically. And so if those two didn't succeed, then that means we found our peak element. Either it means that max index, it means that we found an element that is bigger than both its left and right side, or that we got to the last column, or the first one. In that case, we can't do anything anymore, so we just return max index and the column. So max index is its ith index, and this one is the jth index, which means this is its row index and this is its column index. Okay, and that's all what the algorithm does. So if you can see, it's very similar to the 1D solution. The only difference is that here we find the max, we pick the column, and then we find the max, and the other addition is that we compare to the left. We recurse on the left or the right side. That's the same concept. And then we return the index of that element, which is max index and mid. And that's all. So for example, for this here, if we run it, we can find that the index that is a peak is 3, 2. So that means 0, 1, 2, 3, which means it's here, this last column, and it's 0, 1, 2. So it's this 17 value here, which if you look before the element, it's the peak because it's less than 11. It's bigger than 11, sorry, and which is its left neighbor. It's bigger than 10, its bottom neighbor. It's bigger than 4, its top neighbor, and there is no element on its right. Okay, so that's basically how the implementation can be done. Thank you. See you on the next session. Bye bye.